Hey there, and welcome! Today, we are diving into a scientific technique that is, no joke, everywhere. It's used for everything from making life-saving medicines to solving crimes. It's called chromatography, and it's basically the ultimate tool for unscrambling the most scrambled-up mixtures. Ready to see how it's done? Let's get right into it. Okay, so just imagine you have something like the ink from a pen, or maybe a drop of blood, or even an extract from a plant leaf. To our eyes, it looks like just one thing, right? But in reality, it's a super complex cocktail of all sorts of different molecules. So the big question is, how on earth do you take that mixture and neatly pull apart every single ingredient? Well, the basic idea is actually surprisingly simple, and we can understand the whole thing with just one little story. I want you to picture a race, but this isn't your average racetrack. No, this is a race through a busy, crowded marketplace, totally filled with interesting shops and stalls. This one analogy, this is the key to understanding all of chromatography. So let's break down this molecular race, shall we? We've got our jungled up mixture of molecules, and we're about to send them all running through this marketplace at the exact same time. The real question is, who's going to make it out the other side first? So let's meet our racers. In our mixture, we've got three different types of molecules. First, you've got molecule C, we'll call it the sprinter. It has absolutely zero interest in any of the shops. It just puts its head down and barrels straight for the finish line. Then we have molecule B, the browser. You know, it gets a little sidetracked, stops at a few stalls that catch its eye, but then keeps going. And finally, there's molecule A, the shopper. This one loves the marketplace. It stops at pretty much every single shop along the way. So, as you can probably guess, they are all going to finish this race at very, very different times. All right, that marketplace story gives us the big picture. Now, let's connect it to the actual science. You see, in chromatography, our marketplace racetrack is made of two really important parts, which scientists just call phases. First up is the stationary phase. And yeah, the name says it all. This is the part that stays put. It doesn't move. In our analogy, these are the market stalls, right? The unmoving attractions along the path. In a real lab, this could be a special piece of paper, a super thin layer of silica on a glass plate, or even a long tube packed with tiny little beads. This is the stuff that our molecules are going to interact with. And what's pushing everything along? Well, that's the mobile phase. This is the part that moves. In our marketplace, this is the big, flowing crowd, always pushing all the racers forward. In the lab, it's usually a liquid or a gas, a solvent that flows over or through the stationary phase, and it carries our whole mixture of molecules along for the ride. So let's just map this out to make it super clear. The marketplace shops, the things our racers are interested in, that's our stationary phase. The flowing crowd that pushes everyone along, that's the mobile phase. And our racers, the sprinter, the browser, and the shopper, those, of course, are the individual molecules we're trying to separate. The whole thing works simply because some molecules are way more attracted to the shops than others. And this all boils down to a single property called affinity. You can just think of it as stickiness. So why are some molecules stickier? Well, it often has to do with things like their size or their electrical charge. It's kind of like some molecules have stronger magnets for the stationary phase. Our shoppers with high affinity are going to stick to the shops for a long time and move really slowly. Meanwhile, our sprinters with low affinity will barely stick at all and just get swept along super quickly by that mobile phase. Okay, fantastic. Our molecules have been separated. But how do scientists actually see what happened? How do they read the finish line and know who came in first, second, and third? They use a machine called a chromatograph, and what it does is it spits out this visual report card called a chromatogram. Now, this is a super common mix-up, so here's a little tip. The chromatograph is the machine, the chromatogram is the graph it produces. And this graph, it tells the entire story of our race. Now, the most important piece of information on that graph is something called the retention time. This is literally just the time it took for each molecule to get from the starting line all the way to the finish line detector. It's each racer's official finish time. And what's so cool is that every unique molecule has its own characteristic retention time, which is how we can identify them. So let's check out our race results. Just like we thought, molecule C, our little sprinter, had the fastest retention time, only 2 minutes. Molecule B, the browser, came in next at 4 minutes. And of course, molecule A, our dedicated shopper, took the longest, finishing up at 6 minutes. See that? We've successfully separated our entire mixture just based on their different finish times. Now, a really good, clean separation, what scientists call good resolution, shows up on that chromatography as a series of sharp, pointy, distinct peaks. Each peak is one component, totally separate from the others. If you get these broad, messy, overlapping blobs instead, it could mean your substances are getting all mixed up, or maybe there's an issue with your setup. The goal is always to get those nice, clean, sharp peaks.
You know, just like in sports, there isn't just one kind of race. You've got sprints, marathons, hurdle events, you name it. Well, it's the same deal with chromatography. Scientists have a bunch of different types, and they choose the right kind of race for the specific molecules they need to separate.
The two main categories are planar and column. Planar chromatography is kind of like that classic science experiment you might have done, where you separate ink on a piece of paper. It all happens on a flat surface. It's a great, simple way to separate things like the different color pigments you'd find in a green leaf. Column chromatography, on the other hand, is way more powerful and precise. For this one, the racetrack is a really tightly packed tube, which can be super long. This allows for incredibly fine-tuned separations of really complex mixtures, which makes it absolutely essential for high-stakes jobs, like purifying proteins to make new drugs.
So, we've run our molecular race, we've read the results, but why does any of this matter? Why is this one technique so incredibly important in the real world? Well, the applications are literally everywhere, and you can think of each one as its own high-stakes molecular race. In the pharmaceutical industry, it's a race for purity, to make sure the medicines we take are safe and effective. In food science, it's a race to spot tiny contaminants before they ever get to our plates. Environmental scientists are racing to identify pollutants in our water and soil. Forensic teams use it to separate crucial bits of evidence from a crime scene. Seriously, from creating life-saving drugs to keeping our planet clean, chromatography is this silent workhorse, running these tiny little races that keep all of us safe.
So the next time you see a complex mixture, I don't know, maybe it's the ink in your pen, the sauce on your pizza, or even the beautiful colors in a sunset, just think about that invisible molecular race that's happening inside. Which brings me to a final thought for you. What complex mixture in your world would you be most curious to separate into its purest parts? Thanks for joining me for this explainer.